Motivation is different distributed monitoring and control tasks in multi-report systems where we have multiple nodes that exchange local information to reach some agreement or consensus. And these tasks are used broadly in estimation. We saw some examples in the previous session. Of course, they use it in control, logging, and a lot of other problems. And what the challenge I'm going to consider is what happens if some of the nodes are compromised and they're able to send kind of malicious information in the network. What can we do? Can we show anything that we can still achieve agreement and safety? And how can we characterize this phenomena in the presence of these adversaries? And I'm going to describe just three ideas. The first idea, I'm going to give some overview of some protocols for resilient distributed consensus in the presence of adversaries. I'm going to define some adversary models and describe a little bit the conditions. And we're going to see there is a very big challenge, practical challenge from this type of work. So something we did after that work is try to understand if we can improve the behavior and the resilience of the network if we have some trusted nodes. And then what else can we do with these trusted nodes? And this work has gone here now for a few years. The initial work started with collaboration with Hugh LeBlanc, Sreyas Santaram here, which is here, and one of his students. The most recent work is by Wasim Abbas, which is a postdoc at Vanderbilt, and Eugene Borovetsky. So I'm going to abstract a little bit the problem, so I'm going to assume that we have just synchronous linear iterative consensus, that the nodes they exchange their state information, we take a complex combination of this, and we want to achieve some agreement in the value of the state, and they're all very well-known conditions about when these algorithms converge, and what is the condition of the network topology, this existence of a rooted out branching tree that has to be established periodically over time for the algorithm to converge, which also can be used in case that the network topology is not constant, but is time varying. And these ideas have been used extensively now for many years in many different applications: parameter estimation, least squares, data regression, fault attack detection, and the list goes on and on. And what I'm going to consider is that what if a node in my network is compromised and is able instead to do something in order for this consensus not to be reached and try to kind of degrade the performance and the behavior of the system. So the first question is there a problem? And here is a very simple example. It's a generalization of the very popular Byzantine generals example from distributed computing. It's a network, there are sorcerers and there are 4 generals. And the one general on this square node 4 is Byzantine. So what this general can do can send different information to different nodes. And the scenario is very simple. We have some integrator dynamics where the assumption here is that the state models the morale of the troops. And if it's positive, it's good. If it's negative, it's bad. But this general can send different state information to the different nodes. And it turns out that even in a simple network like that, the malicious node can act as a leader and can drive the value of the consensus wherever the leader wants. So in this case, the blue curves here are the trajectories of the other generals that they believe that everything's fine. And actually the value of all the troops is very low. And then the idea is that even if a single adversary can cause this behavior in the system, what can we do? So that's what we're trying to explore. Now for this example, and just to give you an idea, we're trying to design an algorithm that is going to ensure that all agents are going to converge to the same value, and they're going to satisfy some safety conditions, even in the presence of an adversary, and of course without knowing who is the adversary or what the adversary is. So that's the idea. And basically the protocol is very simple. we're going to consider exactly the same protocol, but we're going to try to find some nodes which we're going to filter out their information. Without knowing who is the adversary, we have to find some kind of rules to understand that keep only the good information. So that's the problem. Of course, there are a lot of variations. So the one typical variation is try to consider different adversary models. And you can have different dimensions to try to characterize these adversary models. The one is the type and the scope. So we can have an adversary that we call a crash adversary. The only thing is going to do crash one of the agents so it doesn't operate. A malicious adversary that has this property that must convey the same information to all the neighbors. So it uses the broadcast model and has to broadcast the same information. And of course, the most general model here, the Byzantine adversary, that can convey different information to different neighbors. And we're going to assume the adversaries know everything about our system, and then the other thing we're going to try to characterize is the scope. How many adversaries do we have? And we have different ways to do that. We can consider an upper bound on the total number of adversaries in the network, or an upper bound in each of the neighborhood of the network, or kind of a fraction in each neighborhood of the network. And we can characterize these adversarial models by considering the network, seeing how many adversaries we have. In this example here, there are three adversaries in the whole network, 3 local in every neighborhood, and 3/5 fraction local. So these are the models that are going to help us to derive some conditions. So, and then in its simplest form, this protocol is shown here. So the main idea is just try to figure out the F maximum and F minimum values, where F is this parameter from the adversarial model. So this, we assume that we know that. And after we remove these values, we just perform the typical consensus algorithm, and we can try to describe the behavior of the overall system. Typically is described by a hybrid system because we can assume that the topology changes with time, and we require 2 conditions. The agents need to agree to the values, so the convergence of the algorithm, and a safety condition that the actual value is going to be in some kind of set that is defined actually from the initial conditions of the agents. So the question is, what happens in this case? When can we guarantee these properties? And in order to do that, it turned out that we needed some kind of new property to capture what we call local redundancy. So the main idea is very simple. If a node talks to many compromised nodes, so then the protocol is not going to work. So we need somehow to assume that each node always talks to some nodes that are not compromised. And we can, I'm not going to give you the formal definitions, but we came with this property, RS robustness, which basically says that for every pair of non-empty disjoint sets, there are at least S nodes and at least R neighbors outside their respective sets. And based on these properties, if the number of adversaries are smaller than some kind of number, we can try to ensure that the flow of information that is needed to achieve consensus. And based on this idea, we can go for different adversarial models, different threats, different scope, and try to derive conditions about when the protocol actually works. And here is some cases. Let me go just one case. Here is a crash or malicious threat model, the F local model, so F adversaries in its neighbor, and we need the network to be F+1 robust. A necessary condition for achieving consensus and to F+1 robust as a fixed condition. And we can basically characterize different kind of networks with this property, robustness of a network, in order to achieve consensus. Now we can go further, and I'm just going to have a slide without details. We can generalize these consensus algorithms to synchronization algorithms in linear systems. So here the idea is the agents are linear time invariant systems, and they want to synchronize so that each agent behaves according to a system here x dot equal a 0 asymptotically, and somebody can basically write down the math and figure out what is the local control shown by this expression in order to achieve this resilient synchronization. And here are the assumptions in order to do that. And now this is the main idea. There is a big problem with this approach. Somebody has to guarantee this property RS robustness. So the question becomes how easy it is to do that. And the definition was not formal, but says for every pair of disjoint sets, which initially says that I have to search a lot. It's very expensive to try to show RS robustness for a particular network, but it's much easier to construct a network that satisfies this property. And here I'm going to give you an example using a preferential attachment model. I'm going to start with a complete graph with 5 nodes, and then I'm going to add each node and 4 edges every round. And then we have developed basically the math that shows that this algorithm is 3-2 robust, so it can be resilient up to a single adversary. So therefore, instead of trying to have a method to compute RS robustness, we can construct robust networks. And then we saw that example, and I think it has to be obvious here that this creates a big problem. We are trying to protect network systems from attacks, and we increase the attack surface by increasing the number of edges. From the practical security point of view, this does not make a lot of sense, because the attack surface is extremely large. So it creates kind of an interesting question. So if resilience needs redundancy, redundancy includes, introduces more problems, so what's going on? I mean, perhaps it's a nice way to increase the robustness of the networks to false, but it's not clear that it makes sense to increase resilience in the presence of adversaries. So we'll try to find ideas. Can we do the same thing? Can we increase the resilience without adding so many edges? So
the question, so
yes.
Is it useful to distinguish between nodes that are compromised versus edges that are being tapped?
Correct. So we can have a different model, different threat model, that just edges are attacked and nodes are not attacked. And I think we'll see in some of the most recent work, the problems are not exactly the same, but are similar.
Right. Why are you unhappy about high connectivity? Because if the nodes are being attacked, why should I care?
Because a node, typically in a network system, is attacked through the network, first of all, remotely. And then the other thing is that for some of the models, typically, let's say we have a wireless network, an attack is going to affect all edges. And it's a little bit abstract notion, but I think it's clear that the attack surface increases a lot. So even if kind of technology is used in order to use kind of spectrum hopping or differentiate between these kind of edges, still the attack surface increases. So at that same time, there was a project going on at the Institute by Professor Karsai, the DARPA F6 program. It was a fractional satellite program. And the idea was to perform a lot of these distributed algorithms in order to have microsatellites, have particular formations, and perform different tasks. And the idea there is they're going to use trusted knowledge. So then we said, okay, what is going to happen if we have trusted nodes in the network? Can we do better? And we came up with an algorithm that basically considers some nodes to be trusted, not to be able to be compromised. And for these nodes, it uses a different variation of the consensus algorithm. And I guess I have to go a little bit faster here. And we came up with this theorem that says if the trusted nodes form a connected dominating set, which means that every other node is connected with them with a one-hop connection and they're connected, you can achieve resilient consensus in any number of adversaries. And we were able to illustrate that with a couple of networks. For example, this network with a traditional algorithm is resilient up to one adversary, but if nodes here 3 and 7 are trusted, so they cannot be compromised, and they always send the correct information, we can be resilient to many more attacks. And these actually results scale well. We consider different random graphs of big sizes, try to understand how many nodes need to be trusted, and so on. So the kind of question here was that if we have a network and we have enough trusted nodes to form this connected dominating set, we can do much better. But if we don't have enough trusted nodes, what do we do? Is there anything between? So we went back and we formulated some of these properties about robust networks in the presence of trusted nodes. So these trusted nodes cannot be removed. And it turns out, even if we have a few of these trusted nodes, we can gain a lot in with respect to resilience. So this is a network. This is not too robust. But if we have one single trusted node, it becomes deeply robust. It can be resilient to certain types of attacks. And then we can go and formulate all the previous results now with these trusted nodes. And the benefit is that we can either have sparse networks with few trusted nodes that have certain resilient properties. And of course the question is, where do we put the trusted nodes? And this is an extremely hard problem, and that's what we're working now. It turns out if you solve this problem, there is a very interesting related problem that you can address. Can I control the connectivity of a graph by placing trusted nodes appropriately? And that's the problem we're looking now. So connectivity of a graph is a very useful property for many different problems. So what we want to do is to control the connectivity by placing strategically a few trusted nodes. So here is an example. So this graph is reconnected because it remains connected if even I remove 3 nodes. And we have the similar results for edge connectivity. So the question is that can we have a different notion of connectivity in the presence of trusted nodes? And I'm just going to present the example. So this graph is 3 vertex connected, so it means that at least I need to remove 3 nodes to disconnect the graph. And I can connect this, I can compute this connectivity with different algorithms, and here is the idea. By placing trusted nodes in the position 7 and 11, the graph becomes 6 vertex connected. So by just adding 2 trusted nodes in the network, I can increase the connectivity. And I can do better with respect to a lot of resilience properties. And of course, again, you're going to ask me, where do I put the trusted nodes? So we have derived some algorithms for doing that. The first idea is based on vertex cuts. It's an exact algorithm that is exponential, but I can use also as baseline. It's not very scalable for large networks, but we're doing also kind of heuristic algorithms based on greedy heuristics. And the other idea that we have developed is that we can start with a connected dominating set of the graph, and we can start removing graphs. and just end up with how many trusted nodes that we have.
So in the context of robotics, place doesn't mean spatial, basically.
No, it means which of my robots are going to be hardened in order to be trusted. Or which of the nodes can be heterogeneous platforms that I have the resources to be, trusted here is an abstract notion, to be more secure in typical attacks. And just in time. So I talked a little bit about this resilience in these consensus protocols in distributed systems. And the idea is, at the end, the message is very simple. I can increase resilience using redundancy, but I get problems because I increase the attack surface. Or I can increase resilience by using trust. What is going on with each of these notions? Of course, somebody can combine them. There is a big question, what is the appropriate notion of trust? Is this definition of trusted nodes that describe the best? But we believe also we can even include other network properties like connectivity that have been used traditionally for different properties of this network system, and we can improve them by placing these trusted nodes appropriately. Thank you.